All right, so in this video, let's take a look at graphing rational functions. I'll have several examples. I'll do one problem per video because these videos take a while to do. All right, so this is a list of the things that we have to go through and find. We need to find our intercepts, our x and y intercepts. So remember to find the x-intercept. You set the function equal to 0 and solve for x. And to find the y-intercept, you just plug 0 in for x and evaluate it. And that gives you your x and y intercepts. You should know how to do that. That's from algebra. All right, and then we look at symmetry. This right here is, we're going to look at odd and even functions. All right, so we know a function is odd if we can evaluate the function at negative x and we get negative f of x back. Okay, that's an odd function. If the function's odd, we know that it's symmetrical about the origin. And then if it's an even function, when we evaluate the function at negative x, we get the function back, the function itself back. That means it's an even function. That function is symmetrical about the y-axis. And then we've got horizontal and vertical asymptotes. So to find your horizontal asymptotes, you just take the limit of the function as x approaches infinity and x approaches negative infinity. And if they approach a number, then your horizontal asymptote would be y equals whatever that limit was. Okay, I'll explain it more as I'm working through the problem. And then for vertical asymptotes, you want to look at the function and see where it's undefined, where the denominator is 0. And then you need to take the limit as x approaches those numbers, numbers. You may have one or two or more. So you want to take the limit as x approaches those numbers where the function's undefined from the left and from the right. And when you take that limit, if it equals infinity or negative infinity, then that means there's a vertical asymptote there. And then you've got slant asymptotes. That you want to check that if the degree of the numerator is one more than the degree of the denominator. And then we've got to look for increasing and decreasing. That's where you take the first derivative, set up your number line, see where it's positive, negative. And then we've got local max min, concavity, where is it concave up, concave down, and then in any inflection points. Okay, so like I said, I know I ran down this list pretty quick. I would just copy it down, and I'm going to explain each step while we're working the problem. Okay, so it'll make more sense. All right, so let's go ahead and get started on an example. All right, so in this example, we've got y equals 8 over x squared plus 4. All right, so first thing, let's find our intercepts. So the intercepts, we've got our x-intercept. Okay, so in order to find the x-intercept, remember, you set the function equal to 0 and solve for x. So if you remember, the only time that a fraction is 0 is when the numerator is 0. So we'll set the numerator equal to 0 and solve for x. Well, you can see in this case, we can't do it. Okay, this will never be 0 because the numerator is always 8. So for our x-intercepts, that would be none. All right. Now, what I would do as you're working through all this and finding all these things, I'm going to write it in a different color, but the things that we need, like all these points that we're finding and increasing and decreasing the intervals we're going to be finding, I would put a star by those. Okay, I'm going to write them in red, but if I were you, I would put a star beside them because that's what you have to go back and use to sketch these graphs. All right. So now let's look at the y-intercept. So to find the y-intercept, we just evaluate the function at 0. And that equals 2. So our y-intercept is the point 0, 2. All right, so that's the first thing. Now, we've got to look at what? Symmetry. All right, so for symmetry, we want to determine, is this function odd or even? So we evaluate the function at negative x. So that's 8 over negative x squared plus 4. And so that's going to be 8 over, and then negative x squared is just x squared plus 4. And you can see when I evaluated this function at negative x, well, what did I get? I got the original function back. You see that? So that tells me this is an even function. All right, so now I know it's symmetrical about the y-axis. All right, now let's look for horizontal asymptotes. All right, so to do that, I take the limit as x goes to, well, let's just go to negative infinity of 8 over x squared plus 4. All right. So hopefully you remember how to find these limits as x goes to infinity or negative infinity. Well, remember, this is just the limit as x goes to negative infinity of 8 over x squared. Remember, you just keep the largest exponent from the numerator and largest exponent from the denominator. If you need more stuff on this, I've got some videos on how to find these, on just calculating limits like this. You can go check those out. So with this, we can see, well, as x is going to negative infinity, well, that's being squared, so this denominator is getting really big. So that's going to 0. And then, so we know right now we have a limit at y equals 0. Now, sometimes when you take the limit of these things as x goes to negative infinity and x goes to positive infinity, you'll get the same answer. But sometimes you won't. So you need to make sure that you do the limit as x goes to negative infinity and as x goes to positive infinity. And I know on this one, we're going to get 0 also. Okay, so that's going to be the limit as x goes to infinity of 8 over x squared, and that's equal to 0 also. So they're the same thing, so we just have one horizontal asymptote. Now, when we took the limit, we got 0, so that means our horizontal asymptote is at y equals 0. All right, so now we need to look at vertical asymptotes. All right, so for vertical asymptotes, we need to see, well, when is this rational function undefined? Well, if you remember that, that's when x squared plus 4 equals 0. It's when the denominator equals 0. And hopefully you can see that if we solve this, we get x equals plus or minus 2i. We get an imaginary number. And I know you wouldn't have to do this. You can look at this and see that the denominator will never be 0. Okay? So there's not going to be any vertical asymptotes. So for vertical asymptotes, that would be none. All right? And then there's no slant asymptotes because remember, for slant asymptotes, the degree of the numerator has to be 1 more than the degree of the denominator. All right. So now we've got to go do what? We've got to do increasing, decreasing, local max and mins, concavity, and inflection points. And what I'm going to do here is I'm going to go ahead and I'm going to write the problem down again just so we can see it. Okay. All right, so now let's look for increasing and decreasing. So to do that, I need to find critical numbers. I've got to take the derivative of this. So the derivative of this, y prime, well, that's the quotient rule. So the derivative of the numerator times the denominator minus the derivative of the denominator times the numerator over the denominator squared. And so this is going to give us y prime is equal to negative 16x over x squared plus 4 squared. All right. Now, we're finding our critical numbers. Okay, remember your critical numbers, that's where the first derivative is equal to 0 or where the first derivative is undefined, provided that those numbers where it's undefined is in the domain of the original function. Okay, but we don't have to worry about that right on this problem about it where it's undefined, because this is not undefined anywhere, because that denominator will never be 0. So what we have to do is we have to take this and set it equal to 0. And as we learned earlier, the only time that's 0 is when the numerator is 0. And so that is x equals 0. Okay, that's our critical number. All right, so now what do? Well, now we have to make a number line. All right, and plot our critical number on the number line, and then we do the test points. X equal -1 and x equal 1. You just have to choose a number from each region. It doesn't matter what numbers you choose as long as it's a number from each region. And so then we have to test that at each of these values, the first derivative. All right, so if I take the -1 and I plug it into here, well, what do I get? Well, I get, let's see, 16 times -1 is -16, and this -16 and this negative is positive. And look, it doesn't matter what I plug into the denominator is going to always be positive. And so when I plug the -1 in, I'm going to get a positive number. Now, I want you to keep in mind here, when we plug the -1 into the second derivative, we don't care about what the exact answer is when we plug the -1 in. All we care about is it positive or negative. That's all we care about. And since we got positive, that means this thing is increasing on this interval here. And then we have to test it out of y prime of 1. So if I plug the 1 in, that's 16 with the negative out here. Well, the denominator's always positive, so this is less than 0. So that means on this interval, it's decreasing. Okay? All right. So I've got decreasing from 0 to infinity, and I've got increasing from -infinity to -1. All right. I'm sorry, not -1. How about 0? That number. All right. So there's my increasing and decreasing. Now let's look for local max and mins. Well, if you look at what we just did here, okay, well, it's increasing here, and then once it hits 0, it starts decreasing. So that means, look at that, we've got a local maximum there. There's no local minimum, but we do have a local maximum. So we have a local minimum at 0. Now, this is where students always mess up. I'm looking for my local minimum. That's a point coordinate. Okay? So I need the x and y coordinate. Well, I've got the x coordinate 0. So if I've got an x coordinate, how do I find the y coordinate? you plug it back into the original function to get your y value. What a lot of students do is they'll plug it back into the derivative. You do not do that. You have to take this and plug it into the first derivative. So if I do y of 0, that's 8 over 0 squared plus 4, which that gives me 2. So there's my, and you know what I did? I realized that now I wrote local minimum. This is a local maximum. Okay. All right. Now we've got increasing, decreasing. We've got our local max min. Now we got to look for concavity. We want to know, where's the function concave up? Where's it concave down? So to do that, we've got to find the second derivative. So we got to take the derivative of this thing. So I've got y double prime. And, you know, for this derivative, I don't know, it might be easier. Let's put the negative up there with the 16x. Is it easier? I don't know, but let's just go ahead and do it. So if I take the derivative of this, that's the quotient rule. So it's the derivative of the numerator, which that's going to be negative 16 times the denominator, minus the derivative of the denominator, so I've got to use chain rule here. Okay, so there's the derivative of the denominator times the numerator, which is negative 16x. And all that over the denominator squared. All right, so now let's simplify this up some. So that's going to be negative 16 times x squared plus 4 squared. And that's going to be plus, what is that, 64x squared times x squared plus 4. All that over x squared plus 4. And, well, look what I did. I didn't square the denominator. Okay. So it's the derivative of the numerator times the denominator minus the derivative of the denominator times the numerator, all that over the denominator squared. Okay? So I just forgot to put the parentheses squared. I got it there now. And then that's to the 4th power. All right, now, to simplify this, it's really not that bad. See how I have an x squared plus 4? I got a common factor on each one, so that cancels. I'm left with the 3rd power there, and here I'm left with the 1st power. So that's going to leave me with negative 16 times x squared plus 4 plus 64. Let's see, 64 x squared over x squared plus 4 cubed. All right. And so then I'll distribute the negative 16 and then combine like terms. And after I do that, I'm not going to go through all that. You should be able to do that. That is going to leave me with 16 times 3x squared minus 4 over x squared plus 4 cubed. And so there's the second derivative, finally. All right, so I'm going to erase the work and then rewrite this up here, and I'll pause the video while I do that. All right, now we've got to set the second derivative equal to 0 and solve for x. So if we set this equal to 0, remember the only time that a fraction is 0 is when the numerator is 0. So really all we need to do is take this part and set it equal to 0. All right, so I've got 3x squared minus 4 equals 0. I get x squared is equal to 4 over 3. So x is plus or minus 2 over square root of 3. Okay? And yes, I know, I'm not going to rationalize the denominator. If you want to, that's fine. To me, it's not a big deal. Okay. All right. So now to determine concavity, we've got to set this up on a number line, and we've got to plot these. -2 over square root of 3 and 2 over square root of 3. Let me rewrite that one. And this breaks it up into 3 regions. And so what we have to do is we have to pick a number from each region. Well, this one's easy. We'll just use x equals 0 here. Now, for the next one, well, let's just punch in 2 divided by square root of 3 in our calculator. That's 1.15. Okay, this is -1.15, and this would be 1.15. All right. So I'll choose x equal -2 and x equal 2. Remember, you just have to pick a number from each region. And then what we have to do is we have to take each one of these numbers and plug them back into the second derivative to see if we get a positive or negative number. So let's do f double prime of -2. And I'm not even going to worry about plugging them into the denominator, because remember, all we care about is it positive or negative. We don't care about the exact value. Okay? So is it positive or negative? That's all I want to know. So I know the denominator is going to always be positive, because whatever I plug into for x here, I'm squaring it, so that's going to be positive. And if you add 4 to a positive number, that's positive. And then this is always positive, so really all I got to do is check this. So if I plug the -2 in, this part will be positive, so that means the whole thing's positive. So this is concave up. And then if I plug the 0 in, well, that's a negative, positive, positive. That is less than 0, so that's concave down. And then if I do f double prime of 2, well, that's going to be positive also, so that's concave up. So I have concave down from -2 over square root of 3 to 2 over square root of 3, and concave up from -infinity to -2 over square root of 3 and 2 over square root of 3 to positive infinity. All right, so now let's look for inflection points. All right, so inflection points, that's where it changes concavity, where it changes from concave up to concave down, or concave down to concave up. Well, you can see it changes here at -2 over square root of 3, and it changes here at 2 over square root of 3. So I've got inflection points at both. Now, to find my inflection points, well, I've got one at -2 over square root of 3, and then I need the y-coordinate, and I've got one at 2 over square root of 3, and then I need to find the y-coordinate. All right, so remember, to find the y-coordinate, we do what? We take these values here, where it changes concavity, and we have to plug it back into the original function, back into y. So I need to find y of -2 over square root of 3 and y of 2 over square root of 3. So I'm going to come over here, and I'm going to do one of them. I'm not going to do both of them, but I'll evaluate one of them. So remember, our function was y equals, what was it? 8 over x squared plus 4. That's our function. So let's evaluate. So I get 8 over -2 over square root of 3 squared plus 4. So that's 8 over, 4/3 plus 4. And so remember, you can look at all these as being over 1. So I'll multiply 3 to each one. So that's going to be what? 24 over 4, 12, what's that, 16? And then 8 goes into them, was that 3 halves? Yeah. So this is going to be 3 halves. And then this would be evaluated the similar. Well, it's going to be 3 halves also. Okay. So now, finally, we found everything. Okay. Now we've got to look at all of this stuff and then sketch the graph based on all of this. So I'm going to erase everything. I'm going to put all the red stuff together so we can look at it, try to look at it all at the same time, and we'll sketch the graph. And I'm going to pause while I do that. All right, so this is about the best I can get it right now. So let's just, I mean, these problems are so much, so let's just look at it. All right, so let's label this 1, 2, 3, -1, -2, -3, and then let's do 1, 2, 1, 2. All right, 1, 2, 3, -1, -2, -3. Now, let's go up here and let's plot the points first. That's usually what I like to do. So we'll come back up here. We've got our x and y intercept. So you can see we've got a y-intercept of 0, 2. And if you come down here, you can also see that's a local maximum. So let's plot the point 0, 2. Okay. And then let's plot our inflection points. So here's the inflection points right here. Remember, we found those. So remember, 2 over square root of 3, that was 1.15, I believe, something like that. It's a little more than 1, so it's somewhere about right in here. And then let's see, the y coordinate is 3 halves. So it's going to be about right in here. And then we've got another one over here. Okay, something like that. And I'm going to explain something. I know I'm plotting all these points and I don't have to, but I'll explain in a minute. So I've got that. So I've got all my points plotted. So now let's look at drawing this graph. So let's look left to right. So I need to see what's happening. Well, and before we do that, we do have a horizontal asymptote at y equals 0. So that's this line here. Y equals 0. That's a horizontal asymptote. All right, so if I look at increasing and decreasing, so really that's what we need, the increasing and decreasing in our concavity. So we got that here. So it says from -infinity to 0. So from -infinity out here up to x equals 0, this thing's increasing. So one thought we may have is, well, you know, how we're going to draw it? We're going to draw it in there like that? Well, let's look. So if we look from -infinity up to this point, the graph, yeah, it's increasing, but it's concave up. And then from here to here, it's concave down. See that? And then once it hits here, it's concave up again. And also, once we get to 0, from 0 to infinity, it is decreasing. So it's going to look like this. And then see how it changes to concave down. And then once it gets here, it goes back to concave up. Like that. Okay, and this graph is not going to cross this line y equals 0. And how do we know that? Because we know we have a horizontal asymptote there. All right. Now, the other thing I wanted to mention, and I could have done this on this problem, but I mean, I didn't, but let's go over it. The symmetry, we determined that this was an even function, so that means it's symmetrical about the y-axis. Okay? So the other way that I could have drawn this is just draw half of this. Just draw this half, and then I can take this part and mirror it over to the other side. And that's the advantage there of knowing if it's an odd or even function, because if it's a lot to graph, you can just mirror it if you know if it's odd or even. And then obviously if it's neither odd nor even, then you'll have to plot all the points and you'll have to draw it up and everything. But hopefully this video helped. Check out my other videos. Give me a like, share, and subscribe, and thanks for watching.